Sure, thank you. And thank you to the organizers of this conference for inviting me to come give a talk. So today I'm going to talk about a mobile app that I use for differential equations. If you are interested in trying it out, it's at www.slopesapp.com. You can go there, and then there's links to download in the Apple Store and the Android store, so Google Play Store. So I'll talk about the app, and I'm going to talk a little bit about some research I did on the class with that app with my wife. So I'll talk a little bit about that too. So just jumping right into it, I want to talk a little bit about the approach that I have to the class when I teach differential equations. I like to really think about it as a models first approach. I want to not just present some differential equations to solve, but to really present mathematical models so that then that will lead us into what techniques we need to analyze and what solution techniques that we will need. So I usually start with physical assumptions for some sort of model. Those become then mathematical expressions. And then I have this idea with the students that I say is think before you solve. So let's look at all these different aspects of the differential equation before we just try to figure out how to solve it. That means looking for equilibrium solutions. That means some sort of graphical analysis like slope fields and phase planes. And then once we've done those things, then we look at if there's a possibility of finding analytical solutions. And I should actually even write numerical solutions down there if we cannot find analytical solutions. So that's generally how I approach the class. So I'm going to talk today about Slopes. Slopes is an app for both now iOS and Android. We released Slopes back in 2016/17 for iOS. But actually recently in January, we finally have gotten an Android version up and running due to popular demand. So this is when I show you the app, this is an app that I've done a lot of programming work for, but is a lot of the programming work has actually been done by students at Pepperdine University. I have a large team of students that I'll be thanking at the end who have been involved in this, and this has been a great project to involve students in. And then, so you ask yourself, why am I looking at doing differential equations on mobile devices? Basically, the fact that they are portable and the fact that they have comparatively large screens over, say, old style graphing calculators and things like that. Those things plus the tactile interface made something like an iPad or an iPhone just a great tool for mathematics in the classroom. Back when the iPad first came out, we did a little bit of research on using some math apps early on in a business calculus class. And from those observations, wrote a research paper about the role of iPads in constructing collaborative learning spaces. And I've found that
without a doubt, one of the best parts of building a tiny house is
that without so I've found that using these devices, students like using these devices, that they're more willing to collaborate using these devices. And so this has been a big part of that of what I've done in differential equations. So most recently, you can find a new paper that I wrote with my wife that we did a research on slopes in the classroom, and that's up online in Primus about some of the stuff I'm going to talk to you about today, and it'll be in print soon, I believe. So let me just jump into slopes. So, oops, okay. So this is the Slopes app on the iPad. It shows a little bit more than it does on the if you're looking at it on the iPhone in terms of things that you can see on the screen at once. But essentially, this is what happens when you open up, say, the slope fields activity. So this is something that I have the students open up basically on the second day of class after we've kind of introduced like what is a differential equation. And then I have basically activities that I've put together so that the students can just explore the world of differential equations and explore these slope fields and just try to make observations. We usually start with some sort of really, really simple exponential growth. I'll change it to growth, sorry. So we usually start with some sort of simple exponential growth, and then I start asking them questions. Okay, they have a slope field in front of them. What do the arrows represent? What are the patterns that they're observing with the arrows? They'll usually say something about the fact that they're all going up, but then you know, they'll notice that the slopes associated with those arrows are getting larger as you move up the screen. So ask them to basically to make these kinds of observations. Ask how the patterns that they see relate to the differential equation and to the model. This particular model that I would have presented them would have been some sort of population growth. You know, does what they see on the screen make sense with population growth? And then I ask them to just tap on the screen to add some solution curves so they can get a sense of like how the solution curves relate to the slope field, and then whether the solutions themselves make sense. So this is the kind of thing that I'd have them do, and then look at some sort of exponential decay and kind of have them repeat the process. Okay, so change a parameter so it's negative, and then we talk about things like chemical decay. And then as we progress through the course, we just kind of keep building on these models. So I might ask them to look at logistic growth. So you can, I should have shown you that. You can see that there are these kind of preloaded examples that are available to you if you, that you want your students to kind of use those. So if we look at like a logistic growth model, I'll ask them some of the same questions, but then I ask them to, you know, put some solutions on and then start describing the behavior that they see for various initial values. Ask them to locate equilibrium solutions and ask them what those things look like on the slope field. And then we start talking about stability of those equilibrium solutions. So you've got a stable equilibrium where there's a carrying capacity, but at zero, you have an unstable equilibrium. You can kind of, obviously it's hard to tap on the screen and just get zeros there. So you can go back in and edit it so that it is just zero there. So then they can talk about things like stability of equilibria there. When I was doing observations, so we did observations of them interacting with the app in class, but we also brought them into focus groups. And I would present them with a new equation, or we presented them with a new equation when they were doing that. I'll show you this threshold model, which is kind of fun. So here they're presenting with a new equation, and I start asking them some of these questions. Describe the behavior of solutions for various initial values. So they'll put some different initial values on the screen. You know, what are the equilibrium solutions here? And then use the plot to describe the stability of the equilibrium. And then I ask them to interpret what's this new parameter C that I put on here. So I've got this new threshold term, y over c minus 1. What is C all about? I like to tell people about this little exchange that the students had when I brought them in for focus group. So what I'm going to do is I'm going to read this exchange to you, but I'm going to put it in the chat so that you have it available to kind of see it. But basically, when I had these students in, the student James, he says, so I asking him about the parameter C. He says, so it would be anything greater than 4. He's probably actually talking about when this population is going to persist. And then Alex is talking about equilibrium solutions, 10, 4, and 0. And James says, oh, and 4 is unstable. It's like the opposite of a carrying capacity. And Dominic interjects, and it's a threshold, right? Yes, it is. So if you're above the threshold, then you go to the carrying capacity. And Daniel interjects, if you're below, you're going to go to 0. And Alex says, it's like the minimum population you need to not die out. And these are all things that they're making these observations on their own, that just by, you know, looking at things like the slope field, having these things available to them, and then and being used to making these kinds of observations in class. So that gives you a sense of how I use the app. I want to just show you some other things about the app that are kind of fun. So let me show you the phase planes activity. So you can look at something like a predator-prey equation if you want. If you click on the screen, it not only gives you the trajectory in the phase plane, but it also gives you what X and Y are as functions of T. You can click on this trace button, and then you can get a sense of how the X and Y versus T solutions, how those relate to what they see in the phase plane. So that there's that kind of stuff that's available for them. At this point, I mentioned that essentially there's a lot of stuff. Once they have this as a tool for the class, one of the things that's great about it is it just kind of reduces the barriers to using technology for things like homework. So they make these plots, they often save them, they can share, export graphs, they can export tables, they can actually share these models with each other. So like you can actually like click on this share model feature, and then like you can text it to people and things like that, and then it will open up the app on their device. So let me get out of that real quick. So a fun new feature that's on this one is that if you can add null lines now to this picture. So you've got other things, other features of a phase plane that you can add essentially to this. In a second, I'm going to mention some things that some projects that the students have been doing with this. One fun project is that if you can adjust this predator-prey equation so that it has what's called density-dependent interaction terms. I just want to kind of show this to you. It takes a second because I'm putting null lines on there. But so if you change the equation so there's these density-dependent interaction terms, okay, so no longer do you have that kind of center that things are orbiting around, but you have actually, you have a sink. You can like put on you can kind of tap and see that the different solutions are approaching that sink. So this is the phase planes activity. And then the last one that students use a lot because they like to do projects is systems. So if you load up a systems activity, you can put up to 15 equations in. This is like the SIR model. This is kind of a default SIR model. I've had students kind of look at, okay, what's going on with COVID-19, and so here's some, you know, you can look at, okay, let's put in some parameters that we think might be relevant to what's going on now, and kind of look at what's going on with an SIR model, just to kind of show you that it's kind of robust, and you I'll put up a Lorenz attractor just so that you can see like that it solves these things in real time, and it can they can kind of scroll through the solution. So the systems activity is something they use a lot for, say, their projects. Let me go back to my slides. I just wanted to mention briefly this thing about semester projects. So that with this app, I have students work in groups of 3 to 4, and their goal is to kind of understand and analyze a mathematical model using the techniques they learned in class. They want to, if it's a single equation, they want to look at slope fields, multiple equations, phase planes, do some equilibrium analysis, these kinds of things. Basically, some of the students will actually create their own models. They'll kind of investigate a topic and do that. Some of them will just investigate a model in the literature, but it gives them a chance to be that applied mathematician. They usually present their final posters as their final presentation, and I bring in a bunch of math and science faculty to have like a little mini poster session. And what happens though is that they can basically rapidly prototype their models because they have they have the slopes app available to them to just start typing in equations. And I just show you, like, this is an example of a project. They were looking at a predator prey with mountain lions versus deer. This is had that density dependent interaction terms in it. If you kind of zoom in on it, so this is the kind of logistic, or yeah, this is the kind of predator prey equation with a logistic growth term and these density dependent terms on it that they were working with. And you can see that they made graphs and things in slopes, and then they did things like looking at the equilibrium and doing some equilibrium analysis with the Jacobian. So this is the kind of work that they've been doing on projects. Just to tell you a little bit about kind of the study and some things that we got from the feedback, we asked them to what extent do they agree with the statement that I feel using slopes increase my understanding of mathematical models in my project. And you can see almost everyone either strongly agreed or agreed. And then a couple quotes to kind of close with. Some of the students have said it's good just because visualizing helps a lot to be able to understand, especially when you get to higher levels of math and things get kind of hard to understand sometimes. And then another one said, I really love how interactive it is. You can move it around and manipulate it. I like being able to click and see, okay, what does this solution with the initial condition look like? So yeah, so that's basically just kind of an introduction to slopes and how I use it in class. As I mentioned at the top, this was a project that I've done with a lot of students. So I guess I've now had 8 different student programmers who have been involved in the project. I specifically will give a shout out to Alex Prieger because he has been working with me to develop that Android version. If you happen to download the Android version, you'll notice it only has those first 2 activities right now, slope fields and phase planes. But I'm happy to announce that there'll be an update by the end of the month that'll get the systems on there. And then I only have time to show a few of the activities, but there's actually a couple more on the iOS version that we're going to be getting to soon. So yeah, I really wanted to end early so that people could ask some questions. There's a companion app to this called Waves that only exists on iOS right now that does some first order PDE stuff. I mean, there's some like heat equation, wave equation kind of stuff. So yeah, that's it. So are there any questions?
Thank you, Tim, for the great presentation. Any questions for Tim?
Yeah, I have a question. Can you recommend something that works on the desktop?
I have.
I mean, I really
no,
like.
I mean,
I really like what you did.
Right. Okay. So one of the projects that I need to do this summer is I can get this to compile on a Mac desktop, and there's kind of this like automatic thing that will be able to do that. But I don't have, or we haven't tried to make a desktop version of this because we've been writing this in the native languages for the iPhone and for the Android because we want them to work smoothly. Like we want these apps, I mean, especially if you put in fairly complicated equations, you can get things to slow down. So yeah. So that's part of it. And then the other thing is that I've been using the mobile devices because I've found that when we were doing things with desktops in class, and this may be different when they're working on homework, but in class, when they were using desktops, then they have these picket fences essentially that are formed between the students. And so that's why we've kind of focused on the mobile apps for now.
Thank you.
There's one thing I see in the chat. Alvaro Ortiz said you can use an Android emulator and run it from a desktop.
So
We have not tested that, so we have no idea what that would look like.
So I'm curious. You the apps are great, and I'm playing with it right now on my iPad. But do you actually have like worksheets such that written up for asking the students questions, or do you just have them play around with it?
I do have some worksheets that are up. I believe that they're available on slopesapp.com. That I have some. Just those are just starting ones that could kind of help you get an idea of how they play around. There's a resources tab on there, and I just have some PDF files of some worksheets that I've created.
Okay, great.
If
I found
anyone
that
ever
too.
wanted, yeah, if anyone ever wanted some LaTeX that went with it, I'd be more than willing to email that to you offline.
Thank you. And do you have a problem in class where not all of your students have an iPad or a phone? I mean, I guess it works on a phone too, so.
So the biggest problem that we had was that it didn't work on Android. So initially I had a class set of iPads, or at least enough for them to work in groups with. Then we got it working on the phone. And at my university, and I know this is very different than others, I would have a class of say 25 and 22 of them would have an iPhone. So it wasn't as much of an issue, and I would lend out a few iPads. But now with the fact that it works on the Android, we're pretty much covering everyone at this point. But I also do bring iPads when I have live classes, which hasn't been for a little bit.
Yeah.
I bring iPads to class so that they can use that bigger version and they can collaborate a little bit more. But a lot of them really like doing it on their phones, and which I never quite understood. But I'm just trying to kind of roll with what the students like to do.
Have you tried it in a virtual classroom right now?
We did use Slopes last semester, and the students would share their screens sometimes with the phones, or they would just have conversations and then hold up their phones to the screen and say, "Hey, look, see, this is what I saw," that kind of thing. So they were able to have discussions online, either by sharing their screen or just having verbal discussions.
Great, thanks.
Hey, Tim, a final question before.
Yeah.
The students you're shown, all those are math majors or computer science majors, or what type of majors they are on?
Yes, so the students who were involved in the programming were all either math or computer science majors.
Okay.
In fact, the last student on the list was a high school student who just emailed me and wanted to do some math. And I said, "Hey, would you like to help me figure some stuff out?" And so he helped me figure out a good efficient algorithm for getting that null Kleins feature up and running. So yeah,